Hi guys, this is physics lesson 4.05, Newton's third law. Well, we've done so far an object at rest stays at rest and an object in motion stays in motion unless acted upon by an unbalanced force. That's Newton's first. Second, force equals mass times acceleration. And the third is that every action has an equal and opposite reaction. I usually start this one off by asking somebody, if you hit your little brother, what happens? And the answer is he hits you back. But the only difference is if he's your little brother, maybe not with the same amount of force that you did. So Newton's third. Every action, or in this case, we could say every force has an equal and opposite reaction. And in this case, we're always talking about forces. So let's take a box on a table. Before we do the box on a table, let's talk about this kind of qualitatively. So if you hit a baseball, the ball exerts, if the baseball exerts a 10 Newton force on the ball exerts a 10 Newton force back on the bat. If you run into the side of a building with 50 newtons, you exert a 50 Newton force on the wall, and the wall exerts a 50 Newton force back on you. So we call these action-reaction pairs. So for example, let's write down what we just talked about. The bat does 10 newtons on a ball. The ball exerts, and we have to change the sign because it's equal but opposite. Negative 10 newtons on the bat. If a body, because you're running, does 50 newtons on a wall, the wall does negative 50 newtons on the body. So that's pretty simple, but we have to consider something. So for these action-reaction pairs, I'm going to do colors, like blue will be one action-reaction pair, and green will be the other. And let me say something about our, so we're going to draw some vectors on this box, and it's just sitting on the table. So let's take a second and tell me what forces are acting on the box. If you want to pause the video, I'll pause for a second. So forces at work here. I'll switch to blue. We've done this before because we had a box on the ice. Hopefully you said we have gravity and we have the normal force, which is the table. All right, now usually everything has to be drawn from the center, but I'm going to put one set of forces here and one set of forces here to kind of make it a little more understandable. So we have the normal force, which is the force of the table on the box. So I'm going to rewrite this as FTB. That means that the box has to exert an equal and opposite force. So let's see, that's about, hopefully those are, so that's the force of the box on the table. All right. Well, what about gravity? So I'm going to set these over here. Remember, I told you we'd be doing force of weight. So this is the force. And it's actually the gravity. So when we talk about gravity, when we talk about it in general terms, we're talking about the field force that exists between the Earth and all the objects on it. So here we're really talking about the force of the Earth on the box. So I'm going to rewrite this as FEB. Well, we have an equal and opposite. So what does that mean? That means that the box is actually pulling up on the Earth. So this is force BE, force of the box on the Earth. Well, what we have here is the two forces in blue are an action-reaction pair. The two forces in green are an action-reaction pair. So this is an action-reaction pair. And these are an action-reaction pair. What we have to be careful of is to understand that when we're analyzing the forces on an object, we're looking at external forces. Forces on an object and by an object are two different things. So let's add two terms here. We have external force, and that would be force of the table on the box and force of the Earth on the box. These are forces on the object. Then we have what are called internal forces. That's going to be the force of the box on the table and the force of the box on the Earth. And those are forces exerted by the object, capital underlined. In the next lesson, we're going to talk about free body diagrams. So free body diagrams show external forces only. So one of the common thought problems you'll run into is that people will say, well, if a horse is pulling on a cart, the cart really shouldn't ever move because there's an equal and opposite force of the cart on the horse and the horse on the cart. Well, what the incorrect statement there is you're analyzing an action-reaction pair. You're taking one external force and one internal force. If you're going to analyze motion of an object, you have to look at all of these, all of the external forces. That's where it's at. After this chapter, we won't mention internal forces again for the rest of the year. Now, it's important to know Newton's third law, and it might show up on an AP test, but it's really not that useful for us unless we're talking about sometimes when we have systems that have multiple objects, then one internal force can also be an external, but that's down the road. But don't make the mistake of thinking that because if we're looking at something and it's accelerating, that the forces are balanced because of the internals, externals. You have to separate these two, but you also have to understand what an action-reaction pair is. So our takeaway is that Newton's third is every action, in this case force, has an equal and opposite force that make up an action-reaction pair. But you have to understand that one half of that is external and one half of that is internal. And when we do free body diagrams, we're only looking at the external. All right, that's all we have for this one. Thanks for watching. Have a good day.